Hello? You're almost done. This is we're third from the last here. The title of this talk is The Young Age of the Lamp-Observed Frost in the Lunar Polar Craters. And the lamp-observed frost, we're talking about that thin veneer, maybe, with lamp penetrates about a half a micron to a micron into the soil. And so we're talking about that very thin veneer at the very tippy top, that frost right at the very tippy top on polar crater floors. I'll mention that this is actually a combination of teams here. Our COIs make up the Dream 2, Impact, and Vortice teams, so there are 3 survey teams, along with LRO and LADI all participating in this. It's really great, quite a group coming together here. Let's see. Whoop, I did something. There we go. So by now we're all familiar with these 2 plots. In particular, this is the water thermal stability model based on temperature in the South Polar region, page and all 2010. The white areas represent places where the temperature is so cold that water frost could be stably trapped within the polar crater. And by stable, we mean that the ice loss rate would be less than a millimeter per billion years. Now, 2015, Paul Hayne actually published this map from the LRO LAMP. This is probably the corresponding map in that top 500 nanometers. And actually, as Amanda talked about, what we're looking at here is the off-on ratio here. If you look at 165 nanometers and the region below that, UV reflectance off of a surface is actually really, really low, whereas 165 nanometers and above, UV reflectance is actually pretty high. And so if you compare bands below and above 165 nanometers, you can actually get an indication of the frost in these polar crater floors. Off-on ratios greater than 1.2 are typically indicative of icy regolith that's greater than about 1% or so from Paul's paper here. And again, we're looking in that top, micron or so. Now, what's interesting is, for example, Hayworth has a pretty nice connection here, but if you actually look at Shoemaker, it's not as much frost. Same with Faustini. So it suggests that temperature is a driving factor, but there may be other processes. And Elizabeth Fisher talked about this as well, looking at Lola brightness, that temperature wasn't the only factor. There's maybe it's the 0th order parameter, but there's something else going on. And the other thing that might be going on is any low-density icy regolith is exposed to other elements of the space environment, including solar wind plasma sputtering, micrometeoroid vaporization, and impact ejecta. And this should have an effect on redistributing the surface ice. And in particular, maybe the ice isn't quite as stable as we think of when we just think of it in terms of temperature. And again, I think of these as sort of corpuscular disruptions where micrometeorite comes in and boom, and disrupts that local region, redistributing the ice. Same with sputtering at sort of the atomic level. And again, this is sort of a cartoon of what I just said. You have a 1% icy regolith, but then you plasma sputter it and particles and the water gets removed. Impacts come in and vaporize and actually move entire chunks, as Laddie Eldex tells us. Okay, so let's take a look at how much water actually gets released by these processes in polar crater floor. Let's take sputtering. Now, the sputtering rate is equal to the yield times the solar wind influx into the polar craters. And I have a number here, about 8 times 10 to the 7th waters released per meter squared per second, using yields formulas from like Bob Johnson's book. What's interesting here is the flux, the solar wind flux. Only about 1% of the solar wind flux gets diverted into the crater. Remember, you have to remember the solar wind is a collisionless gas. So as it passes over the crater, in theory, none should get in. But in fact, what happens is electrical forces force that solar wind into the crater. And we have some models of this. This is why we'd love to have a plasma package in and around obstructions up in the polar region, because we could actually make direct measurements of this effect. But you find that the ion current, the solar wind ion current flux to the surface is about 1% in the center of one of these polar craters, based on some of these models that we've done. So the next process is micrometeorite impact vaporization. Centala 92 actually had some values for this, but they've been recently updated. Porcini and all 29 talks about 10 to the minus 14 kilograms per meter squared second being released by impacts in the form of vapor. And if 1% of that is water, then that's about 4 times 10 to the ninth waters per meter squared second, about a factor of 100 more than sputtering. But the most potent process here, actually, I would normally have stopped my talk there, but thanks to Laddie and LDEX, we now realize that impact ejecta, micrometeoroids come in and particulates go back out, and Laddie measured these, really kind of defined the environment, this new environment at the moon. And Jamie Soleil just actually did some modeling, and even though Laddie didn't get up at the poles, he looked at micrometeoroid sources, sporadic meteoroid sources at the poles, and found that you could get a flux of about 13 ejecta particulates per meter squared per second. And the average size of these grains are actually about a half a micron, actually kind of the layer that we're looking at with LAMP, giving an upward flux that you can calculate here, about 7 times 10 to the ninth waters released per meter squared second for a 1% icy regolith. And this is from Jamie's paper, just came out. Again, he actually, Laddie LDEX measured this helion and antihelion and apex source, and then he added in the north toroidal and south toroidal sources. These are debris fields left from high inclination Halley-like comets, and you finally get about impactors. So this is the entire global impact ejecta environment modeled here. About 13 per meter squared per second of these smaller particulates going up into the exosphere. So what I'm showing here is I want to compare now the thermal and non-thermal processes. What I have here is sort of the Watson, Murray, and Brown sublimation rate here, updated with the Andreas 2007 pressure. And what I also include here is desorption. In the polar craters, it's not clear if you have a sublimation process or a desorption process. They're actually different. But if you have a desorption of water with an activation energy of about 0.46, which is about water sticking to ice-like surface, they actually kind of have a similar path. Here, we calculated this using the first-order Polanyi-Wigner equation that I think Tom Orlando talked about on Monday. What's interesting is if you actually have higher binding energies, you get less, of course, get less water desorbed. So a complex grain might actually have like sort of an integral across these curves here. You can compare these thermal processes to the non-thermal processes we were just describing, and you can see right around 105 degrees Kelvin, impact ejecta and impact vaporization dominate over thermal processes. And in fact, down at 80 degrees Kelvin, you're nearly different by about a factor of 10 to the 6th. In other words, at low temperatures, we can't really think of this top veneer as really being stable because the space environment will be disrupting it and kicking waters off the surface. And so this is a little different thinking than thinking that they're really traps and they're trapped there for billions of years. The water's trapped there for billions of years. The space environment has something to say about this. So what we have here are the water loss rates, again, in this LAMP layer, and I'm talking about the top 500 nanometers. There could even be ice below that, but if you just look at that top 500 nanometers, you have about 10 to the 20 waters in that 500 nanometer layer per square meter, and you can then calculate a water erosion time. And you can find that erosion time, that top 500 nanometers between impact vaporization and impact ejecta is about 2 kiloyears. It's actually pretty quick. We're not talking about billions of years here. What's more is you are kicking water up into the exosphere, and you can actually calculate that. And the impact ejecta here, it's actually the water concentrated on the dust grains. The other thing you can calculate is the water fraction returning within 20 kilometers of its source. So imagine you have your polar crater 40 kilometers, and the water source is in the center. This tells you how much water would come back down within the crater floor. And sputtering is very energetic. Only a very small amount comes back. In fact, a lot of it actually escapes into space. It's faster than the escape speed for the moon. Impact vaporization, about 1%. But impact ejecta, these particles, are actually ejected a little slower. And as a consequence, you can get up to 13% raining back down within the crater. So you're distributing the water within the crater itself to other places. So the bottom line here is that the lamp icy regolith that's sensed in that top layer. It has to be dynamic. And once more, most of the material that gets redistributed within one of these larger craters is most likely icy particulates. So this brings us to data. We always like to have some data to back up our modeling here. What I'm showing you here is the off-on ratios from Hayworth crater from Paul Haynes' data set here. Paul Haynes' data set. This area in red here represents the greater than 1% icy regolith off-on ratios greater than 1.2. And here they are in each one. Here's the fractional amount greater than 1.2 in each 1 degree K bin. And of course, at cold temperatures, about 80% of the pixels measured have water, at least 1% icy regolith in it. But what's interesting is even at 140 degrees Kelvin, you have about 60% with icy regolith. And this is not consistent with a sublimation process where you'd have a volatility temperature of about 105 degrees, and you'd expect a lot of water here and no water here. You're still getting a lot of water in warm regions. And so one non-unique scenario is that you might, in the cold regions, have a deposit like Shuai Li's, what he observed, the icy region, where you have 30% icy regolith, and that's being worked on by the space environment, particularly impact ejection, and that's spreading debris into the warmer regions, creating a dynamic thin frost in warm regions that then sublimes or desorbs to find local cold traps in these regions up here at higher temperature. And we refer to this as sort of a debris field model, where again you might have an ice-rich outcrop, again like Shuai's 30% icy regolith. I'm calling it an outcrop because it might even be related to the deeper water reservoir. It could be a place where it actually kind of reaches the surface. Micrometeoroids come in and eject material into what would normally be drier regions away from the ice-rich region. So here's the conclusions. Bottom line is things may be more dynamic in these polar craters than we think, and it'd be great to get a lander in there to look at that. It'd be great to have an orbital asset to measure that exospheric water that we think might be going off. So that's pretty much it.
Hey, Bill, so you said young age, so you didn't actually tell us an age, but we have exposed water ice very clear on Mercury. So is that consistent with all this, what you've done?
Particularly for that top 500 nanometer layer, probably, but there's probably so much ice underneath it that, you're getting the erosion, but there's ice underneath it. But still, you would expect the space environment, particularly particulates and sputtering, to be operating there as well. Yeah.
So how would you have built up those kind of deeper, more concentrated deposits if stuff that gets, deposited right at the surface is so unstable?
That is the billion-dollar question, where that deeper layer comes from. And in fact, if we knew that, we probably would make more decisions about whether we want to mine it or not.
No question, just a comment. I think the orbital observation totally agree with this model, because the spectral feature showing like 1.5 micron shift towards longer wavelengths, that's only consistent with the ice deposited from vapor phase gradually.
Okay, let's talk more about that. Yeah, right, yep.
Very quick. Hey, Bill, so if the frosts are young, then does the fact that Hayworth has frost and the others don't tell us something about the presence or absence of ice at depth, or maybe something about the local environment in those craters?
It could. That's a good question, whether, and that's something to look at, is do a more systematic look at like plasma inflow and micrometeoroid bombardment on a crater by crater basis and understand the sources and losses. I mean, I sort of picture like a continuity equation where very subtle, where equilibrium is just, the difference, you know what I'm saying, just it's very close, sources and losses. And maybe in some cases you get more losses dominating over the sources. In other places, the sources are dominating over the losses, and, yeah.
So Bill, I think there are even faster processes than impact ejector production, and that is electrostatic delivery of fine dust. So I imagine that there is a shovel going in that might protect or might not protect this thin ice layer, but there are other processes that are competing at incredibly fast scales, or possibly operating there.
I agree, and at some point, hopefully, if we can quantify that, we can make it a fourth process here. Yeah, but you did great. I mean, really, the most potent process is your impact ejecta, which Laddie Eldex really sort of defined that environment, and so that's good.
Yeah, I think we need to move on.
Okay.
Dana Hurley, exospheric processes